putting on your jacket. How do you undo it? You take it off. I know that's not a hard question, but you take off the jacket. All right, so if you open a door, what undoes opening the door? Closing it. All right, that's easy, but the idea is that in your everyday life, when you do something, there's always an opposite action to do the opposite. Okay. In math, we have those things too. So for example, if you add 5 to a number, what undoes adding 5? Subtracting 5. I'm just going to abbreviate because I feel like it. If I multiply by 4, what undoes multiplying? Dividing by 4. All right, if I square a number, what undoes squaring? The square root. All right, bless you. Square root. And then this one might cause a little bit of thinking. If I use the distributive property, what undoes the distributive property? Yeah, factoring. You guys didn't take as long on that. You're smart. When I teach regular algebra 2, I have to stand there and then give them an example. So factoring and distributing are opposites of each other. So in math, we don't just call them opposites. We call those things inverse operations. So for example, addition and subtraction are inverse operations. Now I'm not going to do example 3 because it's just solving an equation and talking about how you do the opposite to solve an equation here. But the word inverse we have seen before this year. And we have seen it in situations like example 4, where we have had a linear function. Here it's 4x minus 11, and we have had to find the inverse. What did we do to find an inverse? Where did we start? If I said find the inverse of f of x, what did you do? You know the opposite of distribute is factor. Guess this.
Oh, you switch that.
Yeah, you switch the x and the y's. So this f of x is a y. So remember we wrote this as x equals 4y minus 11. And then we were solving for y. So you would add 11 to both sides. X plus 11 equals 4y, and then you divide it by 4. And when you divide it by 4, we called that the inverse, f inverse of x. And that equation was x plus 11 over 4. Right? Easy, remember doing that? Not too long ago. So that's where we've seen inverses here, right? We found inverses, and then the question is, how did we verify or prove that f and f inverse were actually inverses? What did we have to do? Do you remember? Not graph it. How do we prove two things were inverses? What had to equal x? Kind of. Remember you had to do composition? So you had to compose and do, you had to do composition. Right, you had to do composition, and we'll just say both had to equal x. Now I'm not going to make you do both compositions here, because if we really were trying to prove these were inverses, you would have to find f of f inverse of x, and you have to find f inverse of f of x. And that just seems like a lot of work for not the point of today. So let's just do one of them. You can pick. Do you want to do the composition that I wrote here on the left or the composition I wrote on the right? Which one looks better to you? The left one. All right. So let's find f of f inverse. Right? Normally we would do the other one, but not today. I'm going to save you some time. So let's think about this inverse. Which one goes into the other? The inverse goes into the original. That means you're going to take this x plus 11 over 4 and put it into the original function. So you would write 4. Now instead of x, we write the entire function of f inverse. X plus 11 over 4, then minus 11. And then you would simplify. So what would you guys do first here to simplify? Cancel the 4's. Right, so I can cancel those 4's off. And when I do that, I'm left with x plus 11 minus 11 And then the 11s cancel off, and you get an x. Is x what you want when you do these compositions? Yes. And then, if we felt like it, which we don't, or I don't, we would do the other composition, and you should get x as well. That proves that they are inverses. Right? So we're talking about inverses. So now we're going to flip our page. Yeah. So if you remember, a month or so ago, we did an activity where you grouped up, and I gave you a little piece of paper that had ordered pairs listed on it. And then you plotted those points, you made a line, and then you switched the ordered pairs and did some stuff, and we started talking about inverses that way. Well, we're going to go back to the same idea here, but we're not going to break into groups. So it says when we originally found inverses, we switched the x and the y values. We're going to do that same thing to find the inverse of an exponential function today. So we'll start with the f of x equals 2 to the x. Right? So let's fill in the table, we'll plot those points, and then we're going to graph its inverse. So when we fill the table here, I like to start at 0. What's anything to the 0 power? 1. Alright, so as I go through, 2 to the first power is 2, 2 to the second, 4, 2 to the third, 8, and then 16. If I go back to the negatives, 2 to the negative 1, it's so quiet when you think 1/2. And what's the last box? 1/4. Okay. So we're going to take a second and we're going to plot those points. And we're going to plot negative 2, 1/4. You can just estimate it. Negative 1, 1/2. 0, 1. It's a small little grid, but so we can fit as many points on as possible. 2, or 1, 2, 2, 4, 5, 6, 7, 8, 16. So then once you plot those, I want you to connect the dots and label that function as f of x. So you know that is the function you're starting with, 2 to the x. Now, as you're plotting those, before you move on, let's fill in the box, at least a little bit of the box, right underneath the graph. So it says for f of x, which you just graphed, there appears to be an asymptote. This is a review question. What's an asymptote? Yeah, a line that you approach but never touch. Where is the asymptote for f of x? At y equals 0, at the x-axis here. So there's an asymptote at the line y equals 0. So now, let's get to the point of today. We're going to graph the inverse of that function. And we said the way we do that up here is we switch the x and the y values. So I want you to take this table. All of these x values in this column, they're going to go in the y column. So let's do that. We'll have negative 2, negative 1. And then all of the y values over here become your x values. And once you fill in that table, you can plot the points. So you'll plot 1/4, negative 2, 1/2, negative 1, 1, 0, 2, 3, 4, 6, 8. There you go. All right, and then you'll connect those just like we did. So take a minute there, plot that, and then you can label that graph as f inverse of x. You should get a graph that kind of looks like my pink one up there on the board. And as you're graphing that, where does it appear that this pink graph has an asymptote? Where does it get really close to touching? The y-axis, which is x equals 0. Oh, so, a couple things to notice. Not only did the x and y coordinates of the point switch, but it looks like the asymptotes switched axes. Now, one more thing to think about for this graph. What line do all inverses reflect over? Y equals x. So all inverses reflect over the line, y equals x. I want you to sketch that on your grid. So you can just eyeball it. But remember, that's the line that goes through the origin with slope of 1. So once you graph that on there, you should be able to see, oh yeah, those definitely reflect over that line. So I want you to take a minute. I want you to now graph the one on the bottom. Same process, but let's find the inverse. You have y equals 3 to the x on the bottom. I want you to answer the questions, fill in the table. You can chat with your neighbor if you need to for a second, but I'll just pause here. Your graph should end up looking like what I have on the board here. So double check that you have the right table, that your picture looks the same, your box is filled in the same way. So the pictures look very similar. The one thing we did talk about when we graphed exponentials last week was that this graph in example 6, 3 to the x, it's a little bit steeper than the graph y equals 2 to the x. Right? So it just goes up a little bit faster. The pictures are the same. So we've graphed the inverse of an exponential function. That brings us, when you're done with that, you can flip to the next page, to a definition here. We call this graph, that new pink one we were doing, a logarithm. So, essentially, the inverse, or not essentially, exactly, the inverse of an exponential function is a logarithm. That's what a logarithm is. It's just a different name. So, like when we did lines, when we found the inverse of a line, it was still a line. So it had the same name. The inverse of a quadratic function is a square root function. Here, the inverse of an exponential is called a logarithm. So let's talk about characteristics, and then we're almost done. We'll give you the definition of a logarithm. We'll be done for the day. When I look at this graph, so it's the two pink graphs on the board here. Where are the y-intercepts? Where do they cross, the pink graphs cross the y-axis? That's 0, 1. That's the exponential up here. We're looking at the pink. Didn't we say there was an asymptote at the y-axis? So does it cross? Does it have a y-intercept? No, so there's no y-intercept here. None. What about x-intercepts? Where do these graphs cross the x-axis? Rachel? 1, 0. Right? Both of them crossed at 1, 0. Which, I just want to point out, if I look at the exponential graph here, its y-intercept is at 0, 1. Notice 0, 1, 1, 0. Those are opposite points. So everything about these graphs are switching. Right? So we have y-intercepts, x-intercepts. What's the general trend of the graph? Increasing, decreasing? Pink one. Going up, going down? What's up, Jamie?
Isn't there y-intercept?
Where? On this one?
No, on the other one. But
Yes, on this one there is, but there's no x-intercept.
doesn't that count? It just says about logarithm.
Right, we're talking about the pink graph. Pink is the logarithm. The pink,
Okay.
the inverse is the logarithm. Yep, so we're only looking at the pink graphs. Bingo. Good clarification, it's okay. So what, it's increasing, yeah. Both of these pink graphs are going up forever. So these graphs are increasing. All right, let's talk about the domain of these logarithms. How far to the left does this pink graph go? Doesn't go past the y-axis, which is what x value? 0, right? It starts at 0. Would that be a bracket or a parenthesis at 0? A parenthesis, because you can't ever equal 0. We can get really close. And how far does it go to the right? Infinity. So your domain this time is from 0 to infinity. What is, oops, wrong way. What's the range? Negative infinity to infinity. So if you remember anything about exponential functions, that's actually all the opposite of the other graphs. So what we have is, it brings us to the end here. We have a definition, a formal mathematical definition here. And that definition says if you have an exponential function, y equals b to the x. So in our class today, we did y equals 2 to the x and 3 to the x. Here's how you write the equation of a logarithm. It's going to start with log. Right? Log is how you abbreviate logarithm, obviously. Log, now here's a little different thing. Log, we're going to do a subscript. We call it a base in math. Log base b, so the b is a little bit lower and a little bit smaller. Log base b of y, so y is now back up to the normal level, same size. So log base b of y equals x. Now it looks really funky. I know it looks funky, but you've only known that definition for about 10 seconds, so it's okay if it looks funky right now. If it still looks funky by Thursday or Friday, then we have a problem. But for today, it's okay. All right, log base b of y equals x. So let's spend another minute here. Let's rewrite the equations, right? So instead of just saying the inverse is f inverse of x, let's actually write the equation of these inverses we found as a logarithm. So let's replace f of x with a y right here. Okay, so f of x is the same thing as y, just so we're consistent. The inverse of this y equals 2 to the x that we found is going to be log. Now up here in the definition, I had base b. B was the base of the exponential. So what's the base of the exponential in this part? 2. So it's log base 2 of, well, let's see, I did log base b of, kind of went around this way, of y, so I made a little curly Q. We'll talk about the curly Q more tomorrow, but log base b of y. So I have log base 2 of y equals, I come back around to the x. Now if I had to do the same equation for 3 to the x, if I start as y equals 3 to the x, what would be the base this time? Log base 3 of y equals x. For today, it's always going to be of y equals x. So real quick before we're done, let's go back to the graphs and let's relabel these. You just wrote the equation. So this f inverse graph here, that's your log base 3 of y equals x. So it's not just the inverse anymore, it's a logarithm. And when you go back to example 5, this is log base 2 of y equals x. It'll make a little more sense tomorrow, but for now we just have the definition. So what I need you to finish up with today is I want you to try, it's the very bottom here, just rewrite some of these as logarithms. Right? So for example, if you did number 3, you have f of x equals 8 to the x. You write it as log, what would be the base of number 3? Log base 8 of y equals x. That's what you're going to do for all of them. Change the base. Just get used to writing log with the base. And then I will give you, let's see here,